Hi guys. Today we will talk about the design of columns subjected to axial load and bending load, so combination of the two. So that means if we have some force on a column which is not at the cross center of the cross section, in that case, if we have eccentricity, we will have both axial load plus bending moment, and bending moment will be force times eccentricity in this case. So firstly, we need to determine axial load, which will depend on the type of the cross section, if we have a spiral columns or tied columns. And that is something which we covered in the previous videos. And after that, we need to determine the moment, which will be force times eccentricity, or in this case, eccentricity times 0.85 times phi, in parentheses 0.85 FC prime, which is compressive strength of concrete. We have AG minus A steel plus yielding stress and times steel area. So for this type of columns, we need to use interaction curve where phi Pn will be axial load, and we have phi Mn versus phi Mn, which is bending moment. So moment here is given using this equation. We need to determine what will be the value of eccentricity, and we are using interaction curve that is ACI code. Usually that will be as appendix on any of textbooks which you are using. So firstly, we need to determine what is the value of phi-pn. Then we have phi-mn, then type of column, square or circular. In this case, we have some rectangular cross section, B and H. Compressive strength is given here 4 KSI. We have a yielding stress 60 KSI. So the third step will be material property, and we need to determine gamma. Gamma will be B minus 2 times cover over B if we have square cross section. If we have a rectangular cross section, it will be gamma H minus 2 times cover over H. So on x-axis, we will have Vmn over BH square. It is given in KSI. And on y-axis, we have Vpn over BH, which is stress, and again given as KSI. So firstly, we need to estimate gross area for columns subjected to combined loading. For tie column, it has to be higher or equal PU over 0.4 times FC prime plus reinforcement ratio times yielding stress. To be economical, reinforcement ratio has to be between 1 and 2%. And for spiral column, we have gross area to be higher or equal PU over 0.5, in parentheses compressive strength of concrete plus reinforcement ratio times yielding stress, and rho has to be between 2.5 and 5%. After that, we need to determine a lap splice length, and this will be given depending on the type of column. If we have tie column, lap length will be 1.0 development length and up to 1.3 times development length. And for spiral column, we will have 0.75 development length. So this is lap length reinforcement, which comes from foundation, and it goes up to the lap length in the column. So it looks something like this. This is from footing to the column. Development length, we are using equation based on ACI code, simplified equations for lap length. And we need to check in this case if we have a tall column with excessive length. We need to check slenderness ratio, because in majority of cases we will have buckling or deflection. So to avoid buckling, we need to see the slenderness effect, and this one can be ignored if we have K times L over R to be less or equal to 22, that is for sway frame, and if we have KL over R to be less or equal 34 plus 12, M1 over M2 for non-sway frame. So if KL over R is higher or equal 22, that means we need to design column as a slender column. R here is radius of gyration. That is something which you covered in strength of materials, and that is a square root of moment of inertia over area. So this is the stuff which you will need to check before you're going further in design. And I will show you here how to design a tie-square column to support force of 450 kips and moment of 120 kip feet with the yielding stress 60 ksi and compressive strength of 4 ksi. Length of column is given 10.5 feet and it is in braced frame. So firstly, we need to do estimation of gross area. Since that this is a tie-square column, AG has to be higher than 450 divided by 0.4 times Fs prime is 4 plus, in this case, for a rho or reinforcement ratio, since that it is a square column, we will go between 1 and 2%. Imagine that we are taking 1.5, so it will be 0.015 and times 60 ksi. So with these numbers, we will obtain that b square is higher or equal to 230, and that will give us b to be higher than 15.2, as we are assuming b to be 16, and we will have new gross area, which is 256 inch square. So PU is 450, MU is 120 kip feet, which is 1440 kips inch. So eccentricity will be 1440 over 450, that is 3.2 inch. E over H is 0.2. Now we need to use the interaction curve for a square column. We need to determine gamma. So in this case, gamma H is 16 minus, for concrete cover of 2.5. We have 2 times 2.5, which will give us 11. And gamma will be 11 over 16, which is very close to 0.7. For on x-axis, we have phi mn over bh square, which is mu over bh square. So that is 120 times 12 over 16 times 16 on square, which is 0.352 ksi. And on y-axis, we have pu over bh, which is 450 over 16 by 16, and that is 1.76 ksi. So we have interaction curve 0.6 gamma and gamma is 0.75. So we need to determine what will be the reinforcement ratio. So how we are doing this? X is 0.352. So we have 0.2 and 0.4. Here is 0.3 and this one will be very close to 0.352. So that will be closer here. Let's stay like this. So this one is 0.352. For y-axis, let's check with the reddish. So here we have 1.5, 6, 7, 8, 9, and 2. So we have 76. So it will be somewhere here. And our rho will be between 0.01 and 0.02, very close to 0.02. Let's say rho is 0.018. That is for gamma is equal 0.6. Then we need to check the other interaction curve. Here we have gamma is 0.75. And again, we have for x-axis 0.352. Again, it will be somewhere here. And we have in y-axis 1.76. So 76 will be somewhere here. And this one is very close to 0.015. So estimation or average between the two is around 0.017 times gross area. So this one is gross area of column will give us 4.35 inch square for steel area. Can assume for number 10, which is 5.08 inch square. So in this case, we need to determine the tie bar. If we have number 10 and a lesser value for diameters, for rebar diameter, we are using number 3 rebars for a secondary steel, and spacing of the ties will be B, which is width of the column 16 inch. We have 16 times rebar size, which is in this case number 10. 16 times 1.27 will give us 20.3, and we need to apply one more 48 times the diameter of the tie, which is 0.375, and that is 18 inch. So spacing of tie is minimum of the three, so in this case it will be 16 inch. Now, the next step is to determine lap length for tie column. We said it is the range between 1 and 1.3. Let's assume to be 1.3. So we have for number 10. So this is number 10 rebar, and here is secondary steel or number or our stirrups, which we assume to be number 3. We have concrete cover 2.5, and using simplified AC equation where we have Fy times Ct times Ce, and we are dividing by 20 times lambda square root of Fc prime, and we are multiplying with rebar diameter. In this case, we have 60,000. Ct is according to the table 1, and Ce is for uncoated rebar 1.0. We have 20, lambda for normal concrete is 1, and we have square root of 4,000. Everything is multiplied with 1.27, which means LD is 60.27. So that is the value of development length, and lap length is 1.3 times development length. So in this case is 1.3 times 60 times 27, which is 78.31 inch. So that was the column subjected to axial load and bending moment. And in the next video, we will talk about biaxial bending plus axial load, when we will have two different moments and plus axial force. We'll use again interaction curves, but the procedure how we will obtain the steel rebar size and the number of steel rebars is a little bit different than what we had in case number 2 and case number 1. Until next video, bye.